All right, this is 4.67, which is a modified Atwoods. You have an inclined plane. Looks like this is 39 degrees. Mass A is right here, and that's 2.7 kilograms. This is connected over the top pulley. Mass B is the same, 2.7 kilograms. Mu K is 0.11. Let's see, what is the question? Ignore masses of the frictionless pulley and the cord. Fantastic. As mass B moves down, so this is B over here, this is A. Determine the magnitude of the acceleration of MA and MB given theta is 39. So the acceleration of A is equal to the acceleration of B because they're connected. So as this one accelerates down, this one's going to accelerate up. Okay, so we're going to do free body diagrams again. FG, FG parallel, FG perpendicular, FN. Because this one is moving in this direction, which I can undo that, the friction is going to be opposite that, so you're going to have a force of friction there. It's important that you draw all of the forces, tension, because eventually we're going to, whoops, get out of there. F net is equal to MA. So again, this side's easy. This side, you need to have your picture. So I'm going to apply this times 2. One for mass A and one for mass B. So I got to figure out what that looks like. I have tension there and I have FG there. All right, so I'll do that one first because it's easy. FG of B minus the tension means MB is going to accelerate that much. But we don't know the tension, we don't know the acceleration, so we can't use this one equation by itself. We need a second equation, which is going to be this one over here. Tension's winning, minus FG parallel, minus FF equals MA times A. If I do the addition trick, I can get rid of the T's, and I get FGB minus FG parallel of A. I didn't put that, but I should. That's of A. Minus the force of friction. Again, for A. Oops. That equals MB plus MA, all times A. FGB is pretty simple. It's 2.7. I'm going to leave out units. I don't have a lot of room here on this little iPad. Minus 2.7, 9.8. The parallel component is the sine of 39 degrees. I'm running out of room. Minus mu, which is 0.11. mg, which is 2.7 times 9.8 cosine of theta, because this is mu Fn, and we know that Fn, change to green, this Fn is the same as Fg perpendicular, which is mg cos theta. So we got to add a cos theta there. This entire thing equals the two masses together, which is 5.4. They're both 2.7 times A. My only unknown is A. So if you can be patient, 2.7 times 9.8. Maybe I'll pause. So after doing all the work, I got 1.397 meters per second squared. Again, you probably have different numbers, but I just checked it and it became green, so I'm good with that one. All right, part B of this. I don't know why I'm doing green. Let me change this to black. Part B, what is the smallest value of mu k will keep the system from accelerating? So actually, I wish I didn't undo that. If I went back to the last page, I can do that. Okay, I can. So to the smallest value to keep it from accelerating, this side of the equation becomes 0. And what I can do is substitute mu k here. So if I could copy this, I would, but I can't. So equilibrium means that A is 0, which means this force, which is, and again, I'll change colors. Let's do bright yellow. That means this force here is balanced by these two forces here. Again, the weight of B minus the parallel portion of A minus the friction of A. Again, this is butchered in terms of all these colors, but essentially you're setting this force equal to these two forces here. You do that, you solve for it, and you can get what mu k is. I'm not going to do it. You can.